All right, number 48. Make a logical chain from these statements. I'm going to represent them in symbols because I think that's a little bit easier to do. This is just like we did before with the law of syllogism, where we're going ahead and linking if-then statements. So this says, if I go to the store, then I will buy candy. If I buy candy, then I will not eat my dinner. So not D. If it is sunny outside, so if it is sunny outside, I'm going to use an O, then I will go to the store. Now you can link things, link statements that begin and end in the same letter, basically, the same term. So here I can link, and I used S. Oh no, S is the same one. You can link these two because they both end in C. So if I link these two together, they become S arrow, not D. And I also have this other statement that says O arrow S. I can put this right up here, O arrow S, and now you see they both end in that S, and I can cancel those out. So this statement really can be boiled down to this logical chain, which says, if it is sunny outside, then I will not eat my dinner. Okay. All right, number 49. Determine the lines of symmetry that each figure has. All right, so a square, an octagon, and a circle. So I'm going to see if I can pull out an actual shape here that will help me. Okay, so I'm going to pull out a square. All right, let me go back to my pen. And lines of symmetry that it has. So lines of symmetry are literally lines that go through it that we can fold this figure over and have it still look the same. Because it's a square, and we know that the sides are exactly the same, I can go right through the middle of this in both directions, horizontal and vertical. And I can also actually go through the diagonals, and it will be congruent as well. So here we have 4 lines of symmetry for this square. And square is really a regular quadrilateral, if you think about it. Regular quadrilateral. And so we'll kind of think about that in 1 second when we look at the regular octagon. All right, let me pull out an octagon. We got an 8-sided figure. I think this might be one. Ooh. Let me look at this one. All right, an 8-sided figure. Awesome. Okay. Oop, not what I wanted to do. Okay, so let's look at this. Here we've got our octagon, and I'm going to draw my lines of symmetry through it again. Now I can actually connect the opposite sides to one another, the opposite vertices. So I've got one. I've got another one. Let's do another one. 2, 3, and 4. And we might think we're done, but we can actually go ahead and add some other ones, some completely different ones. We can actually go right through the middle. So that gives us another 1, 2, 3, 4. So now if we look at it, we have 4 black lines and 4 pink lines. We have 8 lines for this one. All right, a circle's a little bit different. Let's get a circle out here. Here's our circle. And the thing is with the circle, you know, we can try to draw the lines anywhere we want. We can start, you know, pretty much anywhere. All these different lines go through the circle. I can keep doing this because really I can begin anywhere and go through it. And so basically now we can say that there is an infinite number of lines. So I want to go back to that whole regular thing. If it is a regular figure, it has the same number of lines of symmetry as the number of sides. So a square is a regular quadrilateral. Quadrilaterals have 4 sides. That's why it has 4 lines of symmetry. Octagon, 8 sides, 8 lines of symmetry. All right, finally, Charlie states the number of degrees for rotational symmetry for a regular hexagon is always a multiple of 60. And a hexagon being a 6-sided figure. So let's get ourselves one of those. Right over here. Regular means that all of the sides are the same. And he's saying it's always a multiple of 60. Well, if you think about it, I can take this figure right here and I can turn it. Okay, I can turn it around and it looks the same. Around, around. I can keep turning it. Well, I can actually turn it 6 times. And that's because it has 6 what we call central angles going from the center out to the sides. It has 6 of these. And we can determine the measure of this central angle by taking 360 degrees, the number of degrees around that central point, and dividing it by n, how many sides there are. So in our hexagon, the central angle is equal to 360 divided by 6, which is 60 degrees. All right, well, this is important because, yes, I can turn it 60 degrees. I can also turn it 2 times 60 degrees, or 3 times 60 degrees, 4 or 5. So any multiple of 60 degrees works. So yes, Charlie is correct.